go ahead and get started. We're just going to finish up the notes for chapter 2, and we'll take a look at chapter 8 tonight as well. Just to refresh your memory, last time we were talking about different things with conversions. So being able to go back and forth between different units of measurement, like 1 foot to 12 inches, 100 centimeters to a meter, those sorts of things. Converting between different currencies, dollars to euros, euros to pesos, different things like that. And if you have the conversion, being able to cancel out all of the units is the key idea there. So if we just do a quick example here. Say we convert 25 meters to yards. And I'll give you some information here. Given there are 2.54 centimeters in 1 inch. So always start off with what you know. In this case, 25 meters.
You convert 25 meters to centimeters,
Mhm.
and then centimeters to inches, inches to feet, and then inches or feet to yards.
Yep, exactly. So if we go from meters to centimeters,
Oh, isn't it 100?
yep, so centi is the prefix for 100. So centimeters would need to go where?
Centimeters goes on top.
Meters on the bottom there. 100 centimeters in a meter.
And then there are 2.54 centimeters in 1 inch.
Mm-hmm.
So centimeters goes on the bottom and inches goes on top.
Good. Okay, centimeters go away then.
And there's 12 inches in 1 foot,
Mm-hmm.
feet on top, inches on the bottom.
Good.
Then there are 36 feet, no, 37 feet in a yard.
No, there's 3 feet in a yard.
3 feet in a yard, so
There's 37.
30, yeah, 36 inches, 37 inches. So there's 3 feet in 1 yard
3 feet in 1 yard. So 3 feet would go
on the bottom.
on the bottom. Just so this foot and that foot there will cancel. And then from there, let's see what the math says.
27.340.
27.340.
3325. If you want the rest of it, but
Yeah. Yep, we can round there. That many yards. Yep. So practical example here, if you were over at the Y, I don't know if any of you go there or not. Have you ever been to the swimming pool over there?
here,
Yep, over at the Y in town. No? It's a 25-meter pool instead of yards there. Most pools are 25 yards, but some are 25 meters. So you might see some differences there. Any questions on that example there? And again, this can be with anything. It wouldn't have to be with units in the metric system or the imperial system. Say we do another one here. How about a currency conversion here? 100 euros to Canadian dollars. This time I'll give you €1 equals $1.1343 US. And then $1 US will equal $1.35 Canadian. Let's have you take a few minutes at your seats here. Let's see what you come up with. Okay, what do we think?
153.142.
153-ish? That's what I got too. So then, just so we have the work up here, start with 100 euros, right? So then if we want to get rid of euros, euros would need to go bottom. And we want to go from euros to based on our conversions that we have.
US dollars.
Yep, euros to US dollars based on that conversion there. 1 euro, 1.1343 US dollars. Euros then go away. So now our answer is in terms of US dollars. We want to go to Canadian. So US dollars on the bottom there, Canadian on top. What numbers where?
$1 US on the bottom and 1.35 on the top.
Yep, that's really over 1. Bottom will just be 1, but then the top multiplied together was what, 153 and some change. Any questions? Okay. Negative to erase. And I believe the last thing we talked about last time was the metric prefixes. But another thing where this comes up a lot is temperature conversions. So whenever we talk temperature, you're probably used to seeing Fahrenheit. So like outside today it was, I want to say around 60 degrees Fahrenheit, for example. But there are some other ones. Celsius, it's denoted by degrees C. If you were in any part of the world besides the United States, that's how you would see temperatures there. The other system for temperature is going to be Kelvin, which is going to be degrees K. Kelvin and Celsius are pretty similar to each other. Kelvin is basically the more scientific form of Celsius. And to give you some background there, Kelvin is based off of what's the coldest temperature that's possible.
In Kelvin?
Or what's it better known as?
Are you playing Hangman yet?
Yeah. Yeah, why not?
A.
Hey. Okay,
T.
T.
I'll say C.
C.
Yeah.
No C, unfortunately.
I.
I. No I.
L.
L.
N.
N. No N.
B.
Yeah. Like, you solved the word at this point.
E.
E.
Absolute.
Okay. Absolute.
There you go. I knew what absolute was in the rest. Absolute. Temp. I don't know.
I'll make you find there. I'll go word
Come on.
Let's see. I don't know if that helps at all.
No.
No?
R.
V. 0.
Absolute zero.
Yeah, but we won't know how.
Absolute zero there. This means 0 degrees Kelvin. And it is the coldest temperature possible.
Like, in the middle. Like,
What is that in Fahrenheit?
yeah, how cold is that?
What's that in Fahrenheit? Well, it's negative 273 degrees Celsius. So in Fahrenheit, we're probably looking at like negative 300 and something Fahrenheit. Maybe close to negative 400. But pretty cold, to say the least.
I'm cold in like 15 years. Yeah.
Actually, let's see what the exact temperature is.
This isn't like something that happens in like nature.
Not on this planet, at least. Yeah. If we start moving away from the sun, we might get to some places like that. Absolute zero in Fahrenheit is negative 459.67
We're
Fahrenheit.
closer to 500 than we are to.
Yeah. Almost negative 500 Fahrenheit.
That's cold.
And for reference, have you ever seen liquid nitrogen? That's usually around negative 320, just to give you an idea.
How do they get something that cold?
How do they get something that cold? Well, they have to remove the energy out of whatever the object is.
Isn't that how they like do dry ice? Like,
Essentially, they'll take carbon dioxide gas and then take the energy out of it, which will, like cooling it actually. So introducing something to the carbon dioxide that will cool it down. The longer it's cooled down, it'll go from gas to a liquid. And then eventually, if it's cold enough, it'll go liquid to solid there.
you just keep this knowledge on hand, like,
Well, I also teach chemistry, so
okay, that makes more sense.
yeah. Yeah, I do a bunch of math courses, but I also do chemistry and physics, actually. Yeah,
Makes a lot more sense.
yeah. But I have a lot of useless information in my brain, so I'll be the first to tell you that. But any questions on what that means, though? Okay. But the idea here, we're going to have some formulas here that will allow you to go back and forth between these different units of temperature. So one that you should know, I think this chalk is just about done. We'll start Celsius to Fahrenheit. The conversion formula Fahrenheit equals 1.8 times degrees Celsius plus 32. So in other words, if you know either the Fahrenheit or the Celsius temperature, you can use this formula to get to the other one. So prime example, if we know it was 60 degrees outside today, 60 degrees could go in for which of those?
F.
F.
So you divide 60 by,
So we plug 60 in for F into that equation.
but that's not what that equals. Wait, now, okay, now I'm confused.
So if we were going to convert the 60 degrees Fahrenheit to Celsius,
Okay,
we can start off by plugging in the Fahrenheit value of 60.
right,
And then if we can solve this equation for C here, that will tell us what it'll be in Celsius. But this 1.8 C, these are multiplied together, right?
so you would have to divide to,
Yep, so you will have to divide to get rid of the 1.8 there.
so are you dividing it by 60? Or what are you dividing by?
Well, eventually it'll be the 1.8 there, but there's one thing we'll have to do first with this 32. If there's a plus there, what's the opposite of plus?
Subtract it.
Subtract it.
So just subtract it from both sides.
Yep, so we have to move that over first. 60 minus 32,
It's 28.
28. 28 equals 1.8 C.
And you divide both sides by 1.8.
Yep. So C equals
15 maybe 5.6.
5.5 repeating, I'm guessing.
Yeah.
5.6 degrees.
Fahrenheit. Wait,
In degrees
oh wait,
Celsius.
that's just C.
Yeah,
Okay.
but that'll tell you how many degrees Celsius that would be. So 60 degrees Fahrenheit is 15.56 degrees Celsius. Any questions on how we went from Fahrenheit to Celsius? Okay. With any conversion, we can always work backwards, right? But don't feel like you have to memorize both equations here. If you know one of them, we can manipulate it to get the other one. So in other words there, if we wanted to go Fahrenheit to Celsius, we can just take this equation and solve it for C. How would you get C by itself?
Subtract 32 from both sides.
Yep. So subtract 32 on both sides, and that would equal 1.8 C. So then to get just a C there,
Divide by 1.8.
divide that by 1.8, and C is now by itself. But do you see how, even if you just knew one of them, you could get to the other one? So that's something to keep in mind there. The other one is Celsius to Kelvin. For this one, Kelvin equals degrees Celsius, so C plus the 273.15 number.
So it would just be 15.56 plus 273.15.
Yep, so in this problem, 15.56 plus the 273.15 would give you the number of degrees in Kelvin. So in this situation, 15.56 degrees Celsius plus the 273.15.
288.71.
288.71. Degrees, now we're in Kelvin. And in case you're wondering, that 273.15, that is the result of absolute zero. Because absolute zero is 0 Kelvin, or negative 273.15 Celsius. So just so you can see how that relates to that there. Any questions on anything with temperatures? Okay, if you ever have to deal with anything that's based on temperature, I'm willing to bet you're going to see it in either this form or that form. In any type of medical setting there. Am I good to erase? Okay. Okay, we can have units of energy and power as well. Energy here. Process of heating up. To cause movement. So what that means there, if we have two objects that are the same size and the same mass, and one is moving faster than the other, which one is going to be warmer temperature-wise? The one moving slower or the one moving faster?
Faster.
Faster. So generally, the faster that an object moves, the more energy it has, the warmer it's going to be. So in other words, when I was talking to you about absolute zero, if you're cooling it down, what's happening to the movement?
Slowing down.
Slowing down. At absolute zero, there's actually no movement whatsoever. That's the temperature in which all movement ceases to move. The unit for energy here is the joule, often denoted as J. And it's a measure of how much an object can move in terms of heat there.
Sorry.
You're good. Say everything good?
Yeah, I'm a firefighter in EMT, so that's just paging.
Okay. I give you a lot of credit.
Someone has some money,
That's not fun though.
you know.
At one point, I was actually a lifeguard back in the day,
Yeah.
and I was just at the pool the one day minding my own business, and there was a yellow jacket nest. And one of them was on like my palm here. Didn't think much of it, and I went to like move my hand to my knee. Stung me right in the knee twice.
Yeah, yellow jackets are mean.
And it hurt for a while, that's for sure. But anyway, there, power is related to energy. The rate at which energy is used. So basically, it's a form of energy, but it's a rate. From your days back in algebra in high school, when you see the word rate there, that means you're typically finding what thing?
Percentage. No.
Can be a percentage. Big mathematical concept.
Slope.
Slope. Yep.
Oh, please don't make us go back to that.
Don't make you go back to that. Oh, I won't.
Okay, good.
Yeah. But just know that when you see right there, that's what it means. That's what you're finding there. And if I wanted to be mean, I could say, here's a line, find the equation of the line, slope-intercept form,
Y equals MX plus B.
bingo. Yep. M equals y2 minus y1 over x2 minus x1. Does that ring a bell?
Very much so.
Very much so.
PTSD though.
PTSD. I get it. But you won't have to do any of that in here.
Yes, we know that.
Yeah. Most of the algebra you'll need is kind of like what we did manipulating the equation earlier. Like Fahrenheit to Celsius. That's about the extent of the algebra that we'll have there. But joules over seconds will be power there. It's a rate of energy over time. And the unit for that is the watt, which is W. So the idea here, if you multiply this unit here by seconds, what happens to the S's?
They go away.
They go away. And you're left with just joules, which is a unit of energy, right? But if I write a K in front of the W there, kilowatts, and we wouldn't have to be in seconds necessarily, say an hour, kilowatt hours. This is a unit of energy here. And 1 kilowatt hour, I believe, is equal to 3.6 million joules. But just giving you another conversion there that you might see in a problem.
Can you just memorize these numbers
Well, you wouldn't have to.
for like exams or something?
Whenever we get to exams, there's actually going to be a sheet that'll have conversions for you there. Yeah. So if there's anything specific like that, I would definitely give that to you. Yeah. Any questions there? Okay, flipping to the back page. Now we've got things dealing with density and concentration. Density, just general idea here with density. From chemistry, density was often equal to something over something.
Mass and volume.
Yeah, mass and volume are the two things.
I forget, is it mass over volume?
Mass over volume. But mass and volume can have different meanings based on the context of the situation. Some of the examples that they give you here are in the notes. Material density. So typically think grams over milliliters or something like that. Population density, think number of people per square mile, something like that. Information density would be for like technology, so think megabytes per square inch or something like that. So density is based on those ideas. Concentration works pretty much the same way as density. Basically, the amount of substance present within another. And there's two big ones that often show up in the medical world. Blood alcohol content is one of them, and air pollution can be another one. With air pollution, do you remember when Canada had all of those wildfires and it looked really smoky outside? Air pollution was up at that point. Any type of patient that has like breathing issues would experience more difficulties under those circumstances there. Any questions there? Okay, and then price comparisons like we did with the, I believe it was Dr. Pepper last time. That would also fall under density. I think amount of money needed to buy an ounce of Dr. Pepper. That's a measure of density. So it can work the same way there. And if you look at that last slide in the notes, there's a couple of hints there when working through any of these conversion problems. There might be more than one answer. There's probably more than one way to get to the answer. That's true with a lot of things. Consider making the problem simpler and then building up to it. If you can estimate anywhere, that might make it a little bit easier to work through. And if something's taking you too long to solve, chances are there's another way to do it. So if you're working on something and it's taking way longer than you think it should, there's probably another way to go about it, is the idea. And that pretty much covers chapter 2. So any questions about anything in this chapter? Okay. With that, if I could have you get out chapter 8 then. I know it might seem kind of random that we're going in this order. But it does relate to what we've been talking about. Am I good to erase? Okay. Chapter 8 is going to deal with exponential astonishment. And basically, this is going to relate to exponential versus linear functions. And it can essentially be described with a picture here. For a linear function,
Up and then straight.
so like up like that, you mean?
Wait, linear would be,
Like some kind of
yeah.
line
a-
like that.
Up, as long as it's like going up as you go across.
Yep, as long as it's gonna be a straight line
Yeah.
of some kind. So that's linear there. So as x increases, y would also increase for linear. But what would exponential look like? All right, so to help you out here, say I start off with this piece of chalk, and then I decide that I'm going to cut it into two pieces. If I were to do that, how many pieces would I have? Two. So we have one to begin with, then we have two. If I take those two pieces and then cut them in half again, now I would have four.
So is it like straight up?
Yep, so the idea, something that kind of looks like that. If the function is, if it's going up, we could call it
Like what?
if an exponential function is going up like that, we could call it exponential something, exponential growth. So if it's going up like this, it's exponential growth. But it doesn't have to always be going up like that. What if we had a situation that was like this,
Maybe declining.
declining? So if it's declining, there's another word we can use for that. Does start with D though.
Descend minus 2 numbers. N,
Close.
M,
Not quite.
D, DK, D.
Decay.
Oh.
Yep. Decay.
How was M close?
Well, I don't know, I was just going with it, so I was just rolling with it. But exponential decay. So the idea going down over time.
Yeah. Just trying to make it better for being completely off.
So the idea there with that, if this was in, say, 16 pieces, and I reduce the number of pieces in half to make it 8. You start at 16, then go to 8. Cut it in half again, 4 pieces, and half again, 2, and then 1. So starting with a lot of pieces and then going down is the idea. But the reason that this is going to be important here, and this chapter will lead us into the next one once we get there. The next big unit that we're going to have after the first exam that we have is going to start getting into some more things dealing with money, particularly compound interest. But exponential functions show up quite a bit with that. The idea, if you're saving for retirement, for example, which of those graphs would you want to have?
The exponential.
The exponential one. Linear will only take you so far. Exponential will make it much of a difference there. So questions about the similarities or differences between the two? Okay, if you could go to the last slide on that page there. There's a couple of situations here that we're going to look at. I'll just put this on the screen so you all know what I'm talking about there. So the number of students at Wilson High School has increased by 50 in each of the past 4 years. If the student population was 754 years ago, what is it today? Is that an example of an exponential or linear function?
3, 9. So it would be 950, but it's going up in the same increments
Yep. So the number would be 950.
each time.
Yeah, so if it goes up by the same amount each time,
It's exponential. Yeah.
so going up by the same amount each time.
Be linear.
So if we have, say, a graph like this. For growth here, we started at 0. We went up 1 over 1, right? So increase of 1 there.
Oh, you're doubling with that.
Now you have an increase of 2. The next increase would be 4, right?
Yeah, so if this is the same, then it would just be linear.
So increase of 1, increase of 1, increase of 1. So that first one is linear. And we established 950 for the number there. Okay, how about the next one? The price of milk has been rising 3% per year. If the price of a gallon of milk was $4 a year ago, what is it now? Question? Answer? Okay. Exponential. Yep. And because it's rising, this would be exponential growth. Yep. 3% per year. So what would it be now after a year? If it helps there, if we're going up by 3%,
Just for 1 year.
just for 1 year. So going up
$4.12.
$4.12. Yep. But increasing 3% means you can multiply it by 1.0 0.03 there. 0.03 for the percent, 1 being the original amount. Remember back in chapter 3 when we were doing like 10% more, 20% less? It's this idea here. Okay, so then 3, tax law allows you to depreciate the value of your equipment by $200 per year. If you purchased the equipment 3 years ago for $1,000, what is its depreciated value today? $400. Yep. What type of function would that be?
DK.
Decay, it is going down.
Explain.
Exponential.
Yeah.
Exponential or linear?
No, linear because it's the same amount each year.
But isn't it going off of the year before?
Well, $200 per year though. So if you start at 1,000, and say a year later we go down 200, right?
But you're going down 200 from 800.
Yeah.
It's not changing the amount of jobs.
So you start at 1,000, then a year from now,
Yes, for this one, you're
we're at 800 there.
The amount you're going down.
Then the next year, another 200.
Yeah.
Third year, another 200. But to help out with this, for it to be exponential growth or decay, it would have to be going up or down by a percent each year. So if it was going down by, say, 20% each year, or going up by 50% each year,
Why didn't you say it at the beginning?
That was an important piece of
Yeah, that
information.
was-
that was an important piece of information.
That would have helped.
And I thought it might have been something you would have seen along the way, but
We just didn't pick up on it.
it's okay. Try to build some things in to keep it entertaining a little bit, so. All right, so then the fourth one there. Memory capacity, state-of-the-art computer storage devices is doubling approximately every 2 years. The company's top-of-the-line drive holds 16 terabytes today. What will it hold in 6 years? Is the question.
Exponential growth.
Yep, exponential growth, because doubling there. So that means you multiply by 2 each time. And we could go through and do the math there. 16 times 2 would be 32, so that's for 2 years. 32 times 2, 64, that would be for 4 years. Just because that happens every 2 years, right? 64 times 2, 128, that would be for 6 years then. So 128 terabytes. Then the last one, the price of an HD TV set has been falling by about 25% per year. If it's $1,000 today, what can you expect it to be in 2 years? Exponential decay. Yep. Going down by 25% means that we could multiply the 1,000 by what number? To go down 25%.
Wait, what? What was the question?
So if we wanted this 1,000 to go down 25%, what number could I multiply it by in here to get it to go down 25%?
0.25.
At 0.25, that would give you how much you would have to go down, right? So if you do that, that would give you $250. So the new value would need to be the 1,000 minus the 250, 750.
525. And 520.
Yep, so then if you do that again, you said 525 is what it would work out to.
No, it would just be 500. If you multiply by 250, or it's like subtracted by 250 again, it would just be 500.
So that would be if we were dealing with a linear one here. But if it's 25% per year,
Oh, then you would multiply 750 by 0.25 again.
yeah.
So it would be 525.
So 750 by the 0.25 would give us
Mhm. 87.5.
187.5.
Yes.
So then the new value would be
562.50.
562.50. Okay, any questions there? All right, everyone good? Okay. Believe it or not, that's the entirety of chapter 8 there. So a very short chapter. So any other questions? Okay, I know we're a few minutes early, but I think this is a good place to stop for tonight there.